Hello everyone. This video we are going to continue our discussion about pushdown automata, and we're going to talk about two different types of pushdown automata: acceptance by empty stack or final states. So there are two types of pushdown automata in terms of accepting the input strings. We can actually design a pushdown automata that accepts strings by reaching to a final state, or design or pushdown automata to accept the strings by empty stack. What does this mean? I mean, so far all the examples that we have seen were a type of pushdown automata that accept the strings by a final state. Basically, it means that you started from the state Q0, and by reading the full string W and the starting content of the stack is the initial token of the stack Z0. If you can reach after a couple of moves, doesn't matter how many moves, after a couple of moves, if you can reach to one of these situations that you are at an accepting state and you have read the full input string, you are going to accept the string. And you can actually see that I wrote the content of the stack to be A, which means that we don't really care what is in the stack. As far as we have reached to one of the final states and we have read the full input string, we would actually say that the string has been accepted. Doesn't matter if the stack is empty or basically actually doesn't matter what is in the stack. So in this case, the checklist that you have checked is that the input should have been consumed completely and you should be in a final state to accept this. In addition to this specific form that, this is something similar to what we did for the finite state machines, that you should read the full string and you should be in a final state. In addition to this, we can actually design our finite or pushdown automata to accept the strings based on the content of the stack by empty stack. We call it by empty stack. So in this case, if you have designed such a pushdown automata, you would say that your pushdown automata is going to accept all the strings that all the strings like W, that if you start at the initial state Q0 and the content of the stack is Z0, if you can reach after a couple of transitions, if you can reach to a situation that you have read the full string, there is nothing remained in the input string, and the content of the stack is empty, it doesn't matter which state you are in, you would say that you accept the that string. So all of those strings W that you can start with the initial state and the content of the stack only the initial token of the stack Z0. If you can reach to a situation that you have read the full string and there is nothing in the stack, everything has been removed from the stack, including Z0. In that case, you would say you accept the string. And it doesn't matter which state you are in. Okay, so this type of pushdown automata doesn't really care about the states. We don't really need a final state. Not only we don't need a final state in this type of pushdown automata, but we can actually see that we don't need different type of states as well. Only one state is going to be enough if you design your pushdown automata to accept the string by empty stack. Basically the pushdown automatas that accept by final state are going to be more, when you are designing your pushdown automata, it actually makes it much easier if you design it based on final state. It's just like you write down some algorithm and you just follow that, just, okay, in this state just push, in this state just, for example, pop, and then go to a final state in an accepting state. But the empty stack pushdown automata basically actually tells you that when you are designing a pushdown automata, your finite state doesn't need to have different type of states. We just care about the actions that you do over the stack. We just wanted to make sure that you read the input stack, and after a set of actions over the stack is empty, and you accept the string. So we will see that these two type of pushdown automata, it doesn't really matter that if you have designed your pushdown automata to accept by final state or you design it to accept by empty stack, and these two types are going to have the same power. I'm going to show you that they are equivalent. It means that if you have designed a pushdown automata that accept by final state, you can convert it to a pushdown automata that accept by empty stack, and vice versa. So before actually proving the equivalency of these type of pushdown automata, these two different pushdown automata, I'm going to show you an example. Assume that we are working on the language of balanced parentheses. Basically the sigma, the alphabet, is going to be just the two tokens, the closing and opening parentheses, right? And we wanted to design a pushdown automata by final state that accept all the strings which are balanced in terms of the parentheses. So this is going to be a pushdown automata that accept by final state. Okay, so you can see that basically in the state Q0, for every open parenthesis that we will see, doesn't matter what is the top of the stack, I just actually push a token to the top of the stack. And for every closing parenthesis, the top of the stack should be an opening matching to that, and you pop it. And you basically only go to the accepting state whenever you have read the full string and there is no token except the Z0 in the on top of the stack, and you go to the final state and you would accept it. It's actually is very intuitive. Now I'm going to show you an equivalent pushdown automata that accept the same language by empty stack. It doesn't have a final state. We actually don't need a final state. So basically this pushdown automata is going to be very similar to this one. The only thing is that we don't need the accepting state, and I'm going to add one more transition over Q0, and that transition basically just remove the Z0 from the stack. So when you are actually doing such a action, it means that without consuming anything from the input string, if you remove Z0, it means that there is nothing in the stack, and if even Z0 has been removed from the stack, you cannot do any other action. So in all the pushdown automata that you design based on empty stack, you should remove Z0 because the stack should be empty at the end. Okay, and it is important that you actually note that after removing Z0, it basically means that we cannot do anything else. None of the there is no transition after you have removed the Z0, because none of this transition can be done, and you are done. If you remove the Z0, it's just like this is the end of the program. You can't do anything else. To make it more clear how they works, how these two different machine works, I'm going to show you how they works on this input string, which is in the language. This is a valid string. Okay, the first one is the PDA that accept by final state. Here I'm actually showing that how the machine is going to work and check all the possible moves for this input string. And clearly this is not a deterministic pushdown automata. This is a non-deterministic one. You can see that at the beginning, we will start at this situation that we are at state Q0. The full string hasn't been read yet. And the token on top of the stack, the only token in the stack is the initial token Z0. So at this situation, there are two possible moves. You can either, because the top of the stack is 0, you can either move to Q1, right, without actually consuming anything from the input. So you can actually reach to this configuration, or you can use these transitions that tells you that it doesn't matter what is on top of the stack, if it is Z0 or if it is L, you can stay at Q0 and push a token L to the stack. Okay, so there are two moves. Clearly this move is going to crash because if after you move to Q1, there is no more action, there is no more transition for Q1, and you haven't finished the input string. So this path is going to crash, this is not going to accept, and you have to continue this state. At this state, there is only one possible transition for us. You are at Q0, and the top of a stack is L, so the only thing that you can do is that you're at Q0, the top of the stack is L, and your input string, your input string is, the next input string is a closing parenthesis. So you have to match it to the top of the stack, remove the L from the stack, and stay at Q0. So there is only one possible move here. At this situation, again, you can see that there is nothing in the stack except Z0. The top of the stack is Z0, which means that you can use this transition and go to Q1 without reading anything from the input. And it is clear that this is going to die again. This is going to crash because there is no transition at Q1. And you haven't read the full string yet. The other action is that you can push a token L to the top of the stack by reading the open parenthesis from the input and stay at Q0. Again, at this situation, there is only one possible transition. You are at Q0. The next token is closing parenthesis. The top of the stack is L. So you remove L from the stack, which means that you have matched a token, an open parenthesis with this closing parenthesis, and you reach to this situation. And at this situation, the only transition that we have is because we have read the whole input string, so we can only move to a state Q1. We have finished the input string, and yeah, we are going to accept the string. So this is the way that we work on a pushdown automata that accepts by final state. You have to reach to a final state and you have to finish the input string. Now I'm going to show you that how the other pushdown automata that accepts by empty stack is going to work. At the beginning, you start at Q0. The full input string hasn't been read. We haven't actually started yet, and the top of the stack is Z0. Based on the transitions that we have here, you have two transitions, right? You can either use this transition to remove, without reading anything from the input string, just remove the Z0 from the top of the stack and reach to this situation. So this path is going to die again, and the reason is that this part is good, that we don't have anything in the stack. The stack is empty, that's good, but we haven't read anything from the input. So you are not done, and you, basically the machine will crash and just reject the string, right? The other possible action is to use this as this transition here, consume one input string, one token, the first token, which is an open parenthesis, push an L to the top of the stack, and reach to a situation like this. At this position, there is only one possible action, which is this transition, which tells you that you are at a state Q0, you stay at Q0, you read this input string, and you pop one token from the stack, so you reach to this situation. Again, here there are two possible transitions. You can either use this transition and remove Z0, and you can see that after removing Z0, you can't do anything else, and you haven't finished reading the full string, so this path is going to be, it will die, so you can't actually accept the string in this path. You have to continue with the other transition from here. That's actually using this transition that push another L to the top of the stack, use the first, actually consume and read the first, the next token in the input string, and push an L to the top of the stack. And here there is only one possible transition, that is popping an L from the stack, reading the next closing, and popping an L token from the top of the stack. And this situation, there is only one possible transition, and this is the transition. That basically is going to be the final transition. It just makes remove the last token from the top of the stack, which is Z0, and you reach to this situation, which is an accepting situation. You have read the full input string, and the content of the stack is empty, so you would accept the string. So I'm going to now show you that it doesn't matter if you design your Pushdown automata by accepting by final state or empty stack. They are equivalent. They don't give you more expressive power. So I'm going to show you that if you have a Pushdown automata that accepts by empty stack, you can convert it to a Pushdown automata that accepts by final state, and vice versa. So these proofs are again constructive proof. So just assume that if you have a Pushdown automata that accepts by empty stack, I am going to, how to convert it to a Pushdown automata that accepts by final state. I'm going to add a new token. Be careful, this token shouldn't be in the alphabet of the stack. I'm going to add a new token and consider it as the initial token of the stack in the new Pushdown automata that I'm going to create. Okay, so this is going to be a new Pushdown automata. X0 is going to be a new token that I'm going to consider as the initial token of the stack. I will add a new state, a new initial state, and just from this initial state, move to the initial state of the original Pushdown automata. And the action is you don't actually consume anything from the input. We just push, in fact, X0. Just make sure that X0 is in the a stack, and over this transition Z0 will be pushed on top of X0. Okay, so now when you reach to any of those situations that you are going to accept the string, and in those situations you remove z0. It means that you are at a situation and you remove z0. You don't have z0, right? You are accepting your pushdown automata by empty stack. But no, in all of those cases you are going to have x0 there, right? Because x0 is there before even z0 has been pushed in this new pushdown automata. What I'm going is that from all of the states in your original pushdown automata, I'm going to add a transition to a new final state. The final state is going to be unique from all the states in the pushdown automata, because you can actually accept a string in any of these states, right? The requirement for accepting is that the stack should be empty. From all of these states, add a transition to an accepting state, and that transition basically just doesn't actually consume anything from the input, so epsilon from the input, but it actually forces you to have x0 as top of the stack, which means that it's just like in your original pushdown automata, the stack is empty, even z0 has been removed, right? In that case, just move to the final state. So we are going to add a transition over all the states, but this transition only moves to the final state if the top of the stack is x0, right? And so this new pushdown automata that has been created is going to accept exactly the same language. All the strings that will be rejected in this new, and all the strings that will be accepted in this new pushdown automata. And you will see that, just make sure that the new initial state, the new initial token of the stack is going to be x0, not z0 anymore. And we have a final state, which is just whatever you call it, p sub f. So the other part of the proof is that I should show you how we can convert a pushdown automata that accepts by final state to a pushdown automata that accepts by empty stack. So just assume that I have a pushdown automata that accepts by final state, right? I can have as many number of final state as I want. It doesn't really matter how many. But to convert it to a pushdown automata that accepts by empty stack, the only thing that I need to do is that just make sure, it doesn't matter from which state you are, just add a new, in all of these final states, in fact, the thing is, you don't know what is in the stack, and you don't care what is in the stack. You only care that you reach to those final states and the input string has been consumed totally, so you would accept the string. But to convert this final, pushdown automata to a pushdown automata that accepts by empty stack, the only thing that I need to do is to just empty the stack at the final states. So I'm going to just add a new state, okay, and move from all of the final states, add a transition from all of the final states to this new state. You see that we don't consume anything from the input. It's just you're moving over epsilon, and we don't care what is the top of the stack. So whatever it is the top of the stack, just remove it. Okay, whatever is the top of the stack, just remove it. Whatever is the top of the stack, just remove it. And in this state, just keep removing all of the tokens in the stack. So without actually putting any constraint over the string or anything, we just remove all the content of the stack. So all the strings that has been accepted by the previous pushdown automata, they are going to be accepted here as well, because we have a transition to remove all of the content of the stack. Here, just one thing that I have showed to add x0 here as well. But it doesn't really matter. You don't really need this x0 to add for this case. But I just wanted to actually keep it formal. Okay, the next topic to discuss is the equivalency of pushdown automata and context-free grammars. Basically, we have already talked about the context-free languages and context-free grammars, that any language which is context-free, we should be able to create a context-free grammar for that. And the pushdown automata is a machine, is the type of machine that accept the context-free languages. So we should prove it. We should prove that if you have a context-free grammar, you can convert it to you can create a pushdown automata that accept exactly the same language. And if you have a pushdown automata, you should be able to create a context-free grammar that accepts exactly the same language. So in this actually slide, you can see that we already actually know that it doesn't matter if you have a pushdown automata that accept by final state or empty state, they are equivalent. We can convert them to each other. And now I'm going to actually show the relationship between them and the context-free grammars, basically how we can prove they are equivalent. So first I'm going to show you how to convert, if you have a context-free grammar, how we can create an equivalent pushdown automata for that. And that is going to be a pushdown automata that accept by empty stack. Basically, the reason that I have discussed about this, the pushdown automata that accept by empty stack, is that all the proofs that we do over the context-free languages and pushdown automata are basically working on the pushdown automatas that accept by empty stacks. This is just like a more theoretical representation for the pushdown automata. So this part of the proof, that proving that for any context-free grammar we can create a pushdown automata, this is a constructive proof. I'm going to show you that if you have a context-free grammar, how we can create an equivalent pushdown automata that accept the same language. So basically which means that all the strings that will be accepted by that will be generated by the grammar, they will be accepted by this pushdown automata. And if there is any string that will be rejected by this pushdown automata, cannot be generated by the grammar. These steps that I've written here is just a verbal explanation of that. I'm going to skip this slide and basically just show it to you over an example. But before explaining the example, I'm going to actually just briefly discuss that what type of transitions we are going to have in this pushdown automata. We have a context-free grammar. We are going to create an equivalent pushdown automata for that, which this pushdown automata is going to accept by empty stack, and we are going to have only one state in this pushdown automata. Okay, so we don't care about the states. The only thing that we care is that is the transition. We are going to create all the transition in our pushdown automata using the rules that we have in our grammar. So what we have as the input is the grammar, which has a set of variables, a set of terminals, remember, a set of rules, and the initial, the starting symbol in our grammar, which was one of the variables, right? We usually call it S. We are going to create a pushdown automata that accepts by empty stack. We are going to have only one state. Basically, one state is going to be enough. We don't need more than that. the input alphabet is going to be all the terminals, right? This is actually telling me that what is the sigma in my Pushdown automata. All the terminals in the grammar is going to be the alphabet, right? The variables are going to be, the tokens that can be pushed to the stack are going to be the union of all the variables in the grammar and all the terminal symbols. So you can push not only variables but also the input input alphabet into the stack. We are going to define this transition function, and what else we have? We don't have actually an accepting state. This Pushdown automata is going to accept by empty stack, and the initial token of the stack is going to be S. Okay, note that S was the starting symbol in our grammar as well. Here it actually tells you that the initial symbol of the stack, what we actually have in the stack at the very beginning, is going to be the same starting symbol that we have for the grammar. All the transition that we need to add can be defined, can be divided actually to two types of transition. I'm going to first explain this one. Basically, these transitions are about the terminal symbols. It tells me that if the input, if you are at a state Q, we only have one state, to be honest, okay? You are at a state Q. If the input string, if the input token, the next input token is A, which is a terminal symbol, which is one of the input alphabet, right? Input alphabet, the sigma. And if the top of the stack is A, you have the same token on top of the stack. The transition is that you just, you actually read this token from the input string and you remove that token from the stack. Okay, so this is for all of the tokens in the sigma or the set of terminal symbols that we have, we are going to have one corresponding transition. And for all of the variables in our grammar, we are going to add a set of transition that tells me that, okay, without reading anything from the input over the epsilon, I'm not going to actually call it epsilon transition, but anyway, we are not consuming anything from the input. If the top of the stack is the variable A, I am going to add one transition for each rule that I have in my grammar in this form. That, for example, if I have in my grammar something like A1, okay, I'm going to have to add one transition that at a state Q without consuming anything from the input, by just seeing variable A, token A on top of the stack, you stay at the state Q, you add this transition that you pop A from the stack and you push the alpha, the right hand side of the rule. So you actually push these two, it doesn't matter how many tokens you have, you pushed all of them to the stack and from the left to right. So it means that if you have a situation like this, I don't know what is in the stack except the top of the stack. So if you are going to have a transition like this, what would happen? So that A will be removed from the top of the stack. You push 1 and then you push A again. So this is just actually the right hand side. Okay, that's all. This is all of the transition that you need to add. All the transitions for the variables and all the transitions for the terminals. So let me show it to you over an example here. Assume that I have a grammar like this. Okay, and I'm going to create a pushdown automata for that. So we are going to have only one state. Let's just call it Q. The starting symbol in the, the starting token of the initial token of the stack is going to be S. And I'm going to first add the, all the transitions for the terminal tokens. The terminal tokens are going to be only 0 and 1, right? And I'm going to add a transition for each of them. That tells me that if you have seen a 0 and the top of the stack is 0, just remove it from the stack, pop it from the stack. Or if you have seen 1 in the input string and the top of the stack is 1, just pop it from the stack. Okay, now I'm going to add all the transitions for first for S. For S, I have two, maybe that's better to start with A. Okay, I'll leave it S for the last one. So I have a variable like A, right? And it has 3 rules. Okay, for each one I'm going to add a transition. The first rule tells me that, okay, if without actually consuming anything from the input, if you see the token A on top of the stack, pop it and push the right hand side of the rule to the stack. So it means that 1 will be first pushed, then A, then 0. Okay, so from you push from right to left so that the leftmost token is going to be on top of the stack. The other rule that I have is this one. So again, without consuming anything from the input, if the top of the stack is A, pop it and replace it with 1 and A. The other transition that I have is the last one is this one, that again, without consuming anything from the input, if A is the top of the stack, pop it and replace it with 0, 1. Okay, I'm done with the variable A. The only other variable that remains is S, and it has two rules, right? The first one is that if you see S on top of the stack, just pop it and push S and A. And the other part is just removing S, in fact. Okay, so without actually consuming anything from the input, if the top of the stack is S, remove it. That's it. This is going to be the pushdown automata corresponding to this grammar. Here I am actually showing it to you over a couple of steps. See, always when I'm actually converting to a pushdown automata, I'm adding this, basically just tells that at the very beginning, S has been pushed to the stack. Basically, S is going to be the initial token of the stack. Okay, so if you see something like this at the starting state in any source, basically just tells you that whatever you write here is going to be the top of the stack, the initial token of the stack. So all the transitions for A, all the transitions for the terminals, and then all the transitions for S. Okay, you can see that here we would make sure that, in fact, when by this grammar would make sure that S will be disappeared from your string at some point, right? And your pushdown automata will remove S from the stack at some point. Okay, now let me actually show you how this pushdown automata is going to work over a string. Basically, what we did by creating this pushdown automata was we basically just tried to simulate the leftmost derivation for each string or on the grammar. Okay, so basically these actions that we have written here helps us to, in fact, simulates the leftmost derivation. If I have a string like this generated by this grammar, the leftmost derivation for that is going to be like this, that S goes to AS, then A goes to, A will be replaced with 0A1, and then A will be replaced by 0, 1 here, and then S will be actually removed. Go to epsilon and removed. So this tells me that how this leftmost derivation tells me how the grammar generates this string. What the pushdown automata that we have created does is exactly just simulating the what would happen in the leftmost derivation. So this is exactly actually showing you this simulation. That let us actually just see that what we are going to do over this string. You start from this situation. We don't have anything except the initial token of the stack, which is S, right? Then, so if you think about all of these actually transitions, the only possible transition that we have, and it's going to actually work, except this one, which removed S, and this is not going to actually generate this is not going to accept the string, is this one. You have to use this transition. So over this transition, it tells me that don't consume anything from the input. If the top of the stack is S, replace it with pop it and replace it with AS. So this is going to be the next step. You can see that this is exactly the first step in the leftmost derivation, right? This is the first step in the leftmost derivation. Then you have A on top of the stack. You can actually go with any of these transition, but the transition that will at the end accept the string is going to be this one. So without again consuming anything from the input string, still we haven't actually read the input string. We are still actually working over this transition. The top of the stack is A, right? Just pop it and replace it with 0A1. So what would happen is that A will be popped from the stack, and 1, then A, then 0 will be pushed to the stack. Okay, so basically this is exactly the second step of the leftmost derivation. Then you would actually the top of the stack is 0. The only transition which is possible for you is this one, which basically is telling you that, okay, the first token of the input string has been generated, and it's just like you have read this one and you are here. Now the first token has been consumed. Okay, the next step is that, okay, I have read the top of the stack again is A. So I should use one of these transitions, right? I can use any of them because none of them is using any input string, but the one that will end up to accepting the string is going to be this one. So let's actually just apply that transition. If I apply that transition, A will be removed from the top of the stack, and 0, 1 will be pushed to the stack, and I'm not going to consume anything from the input. Still, I'm going to be here. So 0, 1 and 0 will be pushed to the top of the stack. You can see that this is exactly the next step in the leftmost derivation, right? We removed A and replaced it with 0, 1. One of the actually rules here, the step that we have done in the leftmost derivation. Then in the next step, the top of the stack is 0. Okay, the only transition which is possible is this one. You have 0 on top of the stack, and you have 0 as the next token. So you will consume it. So you will remove it from the top of the stack, and you reach to this situation. So the next input token is going to be 1. The top of the stack is 1. The next input token is 1. So I have to use this transition. You just match them and you remove it from the stack. The next token in the input string is 1. The top of the stack is 1. Right? The only transition is possible is this one. You just pop 1 from the stack. Then you are done with the input string. What would happen to the stack? In the stack, you only have S. Okay? You can remove it from using this transition. You can remove it, and your stack will be empty, which basically means that you accept this string. And this last action that you have is exactly the last step of your leftmost derivation when you were generating this string. So basically the pushdown automata, basically I'm using basically a lot. Okay, pushdown automata just simulate what we did in the leftmost derivation to generate any string. So whatever is your grammar, how we generate a string, the pushdown automata just simulate that to accept the strings. So let's see another example. I'm going to convert this context-free grammar to a pushdown automata. Again, we are going to have only one state. Let's just call it Q, whatever. And the S is going to be the initial token of the stack. We have the set of terminals, or the input strings, input tokens are going to be A and B. I'm going to add one transition for each one. So if the top of the stack, if the input string, input token is A, and the top of the stack is A, just pop it. Or if the input token, the next input token is B, and the top of the stack is B, just pop it. And we only have one variable, but we have two rules for that. So it tells me that if the top, without actually consuming anything from the input, if the top of the stack is S, you can pop it and replace it with push a B to the stack. Or without consuming anything from the stack, you can, if the top of the stack is S, you can push S and A to the stack. And that's it. This is going to be the pushdown automata for this. Let's see another example. Remember this grammar. This grammar was generating arithmetic expressions with a very limited form of the identifiers. So here the set of terminals, or input alphabet, is going to be A, B, 0, 1, plus a star, open parenthesis, and close parenthesis. Okay, all of these are going to be the terminal tokens in the grammar, right? So all of them are going to be a part of the input, the valid input tokens. So when we are creating the or input or pushdown automata, we are going to have only one state. and you first add all the transition for all of the tokens, for all of the terminal tokens. So if you see A and the top of the stack is A, pop it. If you see B in the input and the top of the stack is B, pop it. If you see 0 and the top of the stack is 0, pop it. If you see 1 and the top of the stack is 1, pop it. If you see plus and the top of the stack is plus, pop it. If you see a star and the top of the stack is a star, you pop it. If you see open parentheses, the top of the stack is open parentheses, pop it. If you see close parentheses, they don't really look like open and close parentheses, but anyway, you please excuse my handwriting. Okay, we have covered all the terminals. I don't have a space, so I'm going to write the rest of the transitions here. So now I'm going to write the transitions for the variables. First, for I, if you actually, without consuming anything from the input, if the top of the stack is I, you replace it with A and I. So I'm reading it from the right to left to actually tell you that I is going to be the top. Without consuming anything from the input, if the top of the stack is I, you can pop it and replace it with B and I. You can replace it with 1 and I. You can replace it with 0 and I. You can replace it with A. You can replace it with B. So these are all the transitions for I. I need to add all the transitions for E as well. So without consuming anything from the input, if the top of the stack is E, you can replace it with E plus E, or you can replace it with E multiplied by E, or you can replace it with E with open parentheses, E close parentheses, or you can replace it with I. So now we have created the transitions for all the rules, all the terminals. We are done. This is going to be the pushdown automata. And the starting symbol, be careful, the starting symbol is going to be E. Just to make sure that it is clear, the starting symbol is going to be E. You can basically try to, for example, generate a string using this grammar, something like as simple as A plus B, for example. This is the leftmost derivation, right? To generate A plus B. Just try to see that how the this pushdown automata is going to accept the string A plus B. It just actually helps you to digest it better. Let's see another example. Create a pushdown automata for this grammar. Is it possible? Can we create a pushdown automata for this grammar? Unfortunately not. This grammar is not context-free language and we cannot create a pushdown automata for that. I mean, no, it became more clear for you that why, I mean, a grammar, a language like this is not a context-free language. If you think about your machine, just think of it in this way, that you can read your string from left to right only once, and you have access to a stack. Can you recognize the strings which belongs to this language or no? You can see that for the number of zeros, this language forces you to have n number of zeros followed by n number of 1 followed by exactly again n number of zeros. To count and make sure that the number of zeros and the number of ones are equal, you can use a stack, right? Remember, we actually, for each zero that you read, you can push it to the stack and keep a token in the stack. Then to make sure that the number of ones is equal to the number of zeros, you can pop those from the stack, pop those all of the tokens. But the thing is, when you reach to this point, you don't have any other indicator to count the number of zeros, remaining zeros at the end, and make sure that they are going to be equal to the number of zeros and ones that you have seen before. The stack is empty, and I don't know how many zeros or ones I have read so far. So now it is clear that yes, the pushdown automata, a machine that reads the strings from left to right and only have access to a stack, cannot actually represent this language. This is not a context-free language. How about this one? All the strings that the length of them are even, and the string has been repeated, okay? Something like 1 1, or for example 0 1 0 1. Can we create a pushdown automata for this language? We know that we can create a pushdown automata for this language, that whatever is the string W, reverse it at the end. This is a palindrome. This is a palindrome with even length, right? Basically, we can do it because we have access to a stack. Whatever is the string W, you can push it to the stack, and your stack is going to be a first in, last out, or last in, first out type of a structure, data structure, right? So the last token that you have read from W, you can match it as the first token of the reverse of W. So it is possible to create a pushdown automata for this string. But how about these type of strings? Can we? No, we can't, because whatever is going to be actually at the middle point, whatever is the inside W, you should actually just read it as from the bottom of the a stack, and you don't have access to it. You only have access to the top of the stack. So this language is not going to be context-free language as well, because we cannot create a pushdown automata to accept it. Let's see another example. How about this language? Is it a context-free language? Yes, this is a context-free language. This is very similar to this example that we have seen here, but the difference is that we don't restrict the number of zeros at the end to be equal to the number of zeros and ones at the beginning. So this is going to be a context-free language. We can create a grammar for that, something like so goes to A, B. A is responsible to generate the first part, 0A1 or epsilon, and B is responsible to generate the last part, which is going to be B0 or epsilon. Okay, this is a context-free grammar for that, and we can create a pushdown automata for that. I mean, I don't want to actually go through that as that theorem and that proof that convert the context-free grammar to pushdown automata. Just forget about that. How we can create a pushdown automata for this language, we can think about it as this way, that this is very similar to the you know, the very first example that we have seen. Just have a state to push all the zeros. Okay, for each zero that you see. It doesn't matter what is the top of the stack. Okay, just consider it as Z0. Just push, let's just use 0. That makes it actually easier to work on later. For each 0, I'm going to push a 0 to the stack. And if the top of the stack is 0, just push a 0 to the stack without consuming anything. I'm actually creating a non-deterministic pushdown automata. For this one, you can create a pushdown deterministic pushdown automata as well. But just to make it easier, I'm creating a non-deterministic one. So if it is Z0, just keep Z0 and move to this state. This state is going to just pop the ones, or if the top of the stack is 0, just don't touch it and move to this state. This state, let's just call this one Q0, Q1. Q1 is popping all the ones that you have pushed. So that's going to be 1, and the top of the stack is 0, pop it. Only pop if the top of the stack is 0. Or you can move, so it's just like we have pushed all the zeros, all the beginning zeros to the stack in the Q0, and then in Q1 we have popped all the zeros corresponding to the ones that we are reading, and then we can move. If we have read all of the zeros and ones and they are all matched, you can move to this state Q3, which is an accepting state, and for all the zeros that you see, if the you see a 0 and the top of the stack is Z0, just keep Z0 here. Okay, so this is going to be the only possible transition. So you can read as many number of zeros as you want here and stay at the final state. So this is a pushdown automata that accepts Y final state. I just designed it in this way because I wanted to actually give you the idea of how to think about the an algorithm for your pushdown automata, not just converting the grammar to a pushdown automata that accepts by final state. How about this one? Can we create a pushdown automata for this? You can see that this language is a regular language. This is not as hard as the context-free languages. This is not even as hard as the context-free languages. So basically, you don't need a stack. So every finite state that you design is going to be a valid pushdown automata as well, because it's just like you have a finite state and you have a stack, but you are not touching the stack. You are not using a stack. So every finite state that you design is going to be a valid pushdown automata, because you can just think about it as a pushdown automata that you are not using the stack. You are not pushing or popping anything from the stack. And I have actually a couple of examples here for you. Just take them as an exercise. I'll try to push the some of them are even actually regular languages, so it doesn't actually really going to be a very difficult problem. Anyway, I'll try to post the answers to the Blackboard. So this is going to cover chapter 6 from your textbook. After watching this video, please read the slides again one more time and try to do the examples, the exercise, and if you had any question, please come to the office hour or email me.